Hello, everybody. So we are from IBM, and today we will be talking about dynamic properties for Apache Spark applications resource allocation, something which we did for our IBM on-prem offering based on Spark. So, and I start from basically from definition of what case we are looking for. So in general, we're looking for a case of the Spark as a service, meaning that multiple tenants submit multiple Spark applications. And then there is service level agreement definition, which actually understood differently from different side of the service. So for the service provider, the service level agreement is actually a requirement for resources like CPU, memory, network I/O, and it's constrained mostly by how much user are ready to pay for these resources. But from the user point of view for these resources, for this service, its service level agreement is basically the requirement for how much time I need to finish my application. So I'm ready to pay more so my application can finish faster. And by application, I mean not only one application, but processing flow pipeline. So in this case, what we think is that the scheduling priorities can be a way to reconcile users' service level agreement with the one used by providers. But because that multiple factors actually affecting the runtime and environment, and it's also changing over time, so it's pretty hard to predict which priority would need to be set when you start in your application. So that's bringing us to having ability to modify priority dynamically on any stage of the running application, even when it's actually pending. And the mission-critical use case we're basically trying to solve with this priorities modification for service level agreement is for pending application when it's need to jump the queues, so called basically start earlier. And for the running application, it's need to get more resources so it can finish earlier to meet some deadline. So this slide is actually from Cloudera about the integration on Spark on Yarn. But we talk generally what we have in terms of priorities for three different major integrations. So for standalone mode, basically it's providing FIFO order and no priorities. For Mesos, it also does not have priority, and it's basically supporting course mode where it's allowing to specify the limit, but basically the first coming has offering to take more resources, so no priority there. For Yarn, Yarn allowing to specify, like for standalone as well, a number of executors and memory, and it has some additional dynamic resource allocation. What that is basically some kind of heuristics allowing to add more request for more resources based on current scheduling round. So it's triggering a request for more resources based on the number of pending tasks for the period of time. It's configurable. But note for the future discussion is that it's not deterministic, it's basically heuristic-based and time-based. And then Yarn has two schedulers, first share scheduler and capacity. The first one has priority based on the queue, so basically it's depends on which queue you're submitting, and it's assigned the priority and you cannot change the queues. For the capacity scheduler, it's supporting priority but only for FIFO or policy. So another thing I want to stop on this slide is basically how it's integrated with Yarn. So basically, idea of Yarn is to separate scheduling from resource management, and for that reason, the first operation when you're starting something on Yarn is creating application manager. And that's supposed to be your scheduler for the scheduling resources, so it can allocate more resources from the Yarn. But in Spark on Yarn integration case, the application manager is basically driver itself. So it's very well handling the case where you have multiple jobs with this from the single Spark context, right? And it has priorities for this case, and so on. But for the case where we have multiple applications, right? Each of them is a separate application manager. So basically, it's offloading the scheduling part again to Yarn, which is not supposed to do this. So that's a major point where we introduce change. So what we did, we took standalone Spark Master, and we enhanced it in a few ways. So first of all, it's fully compatible with a standalone, right? So you submit it like to standalone master. But what it's actually doing, it's scheduling resources between different applications submitted to it, but it's allocating resources from the external resource manager. So we're having two-level scheduling. Another extension we did, we extended the scheduling policy because standalone master, as I just said, has only FIFO. So we added fair share and priority-based policy. And leaving everything else is fully Spark compatible. So basically, in the end, we have this two-level architecture. So we have resource manager layer. In our case, it's our HPC based resource manager, enterprise-grade orchestrator, which IBM has, but it actually can be integrated with Yarn or with other resource managers. And then we have these session schedulers. Each of them is basically modified Spark master, and multiple applications which can submit to one scheduler. And because we have configurable policies, so the policies can be different for different schedulers. So now a few words about that fine-grained scheduling. So as you know, that Spark basically split the job into stages. And this splitting based not only on the application, but also on the data. So the same application when running on the different data, they will have the same stages, but the number of tasks needed in each stage will be different. So at any moment of time, the number of tasks actually needed for computation is different, and the graph on the left showing this ideal demand for the tasks. When it's coming to the actual allocation of resources, so this orange lines is basically standalone or Yarn without dynamic allocation, but dynamic allocation will also change this, not very deterministic. So in contrast, what we're doing, we actually a driver requesting from session scheduler, from Spark master, exactly what it's need for the demand of the task. And then in ideal case where we have, when the session scheduler has everything allocated from resource manager, he can follow this demand. So basically the blue line there, you see very much to the demand. And also in the releasing case, right? So if we don't need, for next stage, we don't need that much resources, we're releasing them. And that's meaning that other application can use it. So overall utilization will be much higher. And actually on previous summit, I had some benchmark there that we can run overall faster mode applications, finishing faster, so utilization can be higher. So as I said in this sessions scheduler, we have added priority scheduling, which is similar to FIFO, just changing the order in which the pending queue will be organized based on priority of the submitted application, and also covering case when you can change priority for already submitted application, which is pending. And then we added fair share, but our fair share is a little bit different. it's taken in account as a weight the priority. So basically, it's changing the ratio in this sharing based on the priority of the submitted application. So by default, all the priorities are equal, so it's fair share, but the ratio can be changed. And to do this dynamically, we introduce another property for this Spark as a priority, which is integer value from 1 to 10,000, and we put in default in the middle of the range, so we can increase or decrease priority from the default. And also two another parameters is reclaim. So basically when we start a new job, a new application to the same session scheduler, or we change in the priority, we basically need to reclaim resources from the already running applications. And it can be done in basically 3 different ways. And this is controlled by reclaim timeout, basically another property which can be configured. And my colleague will talk in the details about this. And we still keep the limits. So we basically, besides the sharing and ratio, we also allow it to cap each application, but how much it can use. So it's somehow similar to a Spark Executor course. And now I give Shinno to present actually more implementation details and also to show small demo on that.
Okay, so let me start explaining about the implementation details. So here I prepared a high-level overview of the Spark cluster. And if you look at the left, we have a Spark client, application submissions, and application updates through RESTful API. And then the priority value is passed from the Spark client to session scheduler, which is equivalent to Spark master in the open source concept. And then within the session scheduler, we have a driver scheduler and executor scheduler. And this priority value that's passed from the Spark client feeds into each of these schedulers. And then these schedulers make scheduling decisions based on this priority value from the client and some other metrics to make resource requests to the enterprise grid orchestrator. So this is equivalent to the resource scheduler concept in the open source world. So it could be Mesos or Yarn, for example. And then the resource scheduler returns resource adjustments back to the session scheduler in the reply, and then the session scheduler actually starts scheduling or reclaiming drivers and executors in the cluster. Okay, so let me start explaining what each component, the details of each component. So first I'll start explaining about the scheduler for drivers. And drivers' resource allocation adjustments are expected to follow first in, first out. But there are some exceptions. And the most important thing here is that drivers are expected to be non-preemptive, meaning when the driver is competing for its resources, it does not preempt other drivers, meaning it does not kill the driver. This is important because if the driver gets killed, then the entire application fails. So even if the application has enough executor slots to keep the application running, if the driver gets killed, then the entire application fails. So that means service level agreements for the drivers can only control the driver's start time. And dynamic application priority is used to adjust the sorting order in the driver's pending queue. Okay, moving on to the executor scheduler. So the Spark application priority is translated by this executor scheduler to resource allocation adjustments for Spark tasks between applications submitted to the same scheduler. And then this priority translation algorithm is determined by a scheduling policy. It could be priority policy or fair share policy. And if you use priority policy, for each scheduling cycle, applications are sorted by their priorities. And then the highest priority application is given all resource allocations that it currently requires for its tasks, and then followed by the next application in a priority order. And if you use fair share policy instead, Then for each scheduling cycle, scheduler calculates the priority weight allocation shares among all submitted applications from the entire resource pool. So if an application currently requires fewer tasks than entitled by its share, remaining resources are returned back to the shared resource pool, and then it's shared between the rest of the applications that use the same sharing policy. And resource allocation adjustments might happen in every scheduling cycle based on the scheduling decisions that it makes in each scheduling cycle. So the rebalancing of resources may happen between applications. And you can configure the behavior of this rebalancing. And it can either be preemptive or non-preemptive. And you can configure this with the reclaim timeout value. And if you set this reclaim timeout value to be 0, Spark driver will kill any running tasks and return resources at once to the scheduler. But if you configure this reclaim timeout value to be something positive, then tasks will be canceled after this timeout value is expired. And if you don't enable preemption, meaning if you operate in non-preemptive mode, then drivers will wait for its tasks to finish before releasing its resources. OK, so now let's look at the client-facing client interface. So we extended the RESTful APIs on Spark Master. And for application submission, hopefully everyone's aware of which REST API that I'm talking about. It's the POST API to submit application to Spark Master. And we extended this POST API with this new optional field priority that can take the value from 1 to 10,000. The default is 5,000. And for the priority update, since open source Spark does not have the concept of updating an application, we added a new RESTful POST API at version 1 submissions update, and then you can put the driver ID or application ID where you want to update the priority value. And I also included sample body and response here. And in the body, you can specify the new action that we added, update submission request, and then the new priority value that you want to use. In this example, we have 10. And in the response, you get the regular RESTful API response. You get the message and success field indicating whether your update request was successful or not. So since all the other Spark RESTful APIs are asynchronous, this update API does the same thing. It's an asynchronous call that only returns the status of the API call. But please note that when this API is used with the driver ID, then we update the priority for both associated driver and application. But if the app ID is used, then only associated application priority value is updated. So what this means is that if you submit application with, for example, a supervised flag set, then if that application fails somehow and then requeues itself as a driver, then the updated application priority value is lost, and then it requeues itself with the driver priority value. OK, so the next 2 slides, I'm going to cover key concepts for enterprise customers. So the first one is authorization. And I think we need at least the following role-based permissions. First one, for authorized users to set and update priorities of their own applications with the valid range from 1 to 5,000. And then the second one for admins to set and update priorities of everyone's applications. And the valid range is, of course, the full range from 1 to 10,000. So what this valid range does is to reserve the range from above 5,000 to 10,000 for admins as a privileged priority value range. so then they have full control over the cluster. So users would have to lower priority values if they want to prioritize and order their applications. Okay, second enterprise key topic for enterprise customers is auditing. And we added the auditing capability in the Spark master log. Here I included the small snippet. And if you look at the first line, it says how the application was registered with the initial priority value of 5,000. And if you look at the 2 lines at the bottom, you see that admin updated the priority value of the application from 5,000 to 10,000 for GPU and CPU resources. So this is where admins can go and check what went wrong and why. Okay, so let's get to the fun part. I prepared some demos. So here we are using a Spark 220 cluster deployed with IBM Spectrum Conductor with Spark 221. And we have one case for driver scheduler and another case for executor scheduler. And the first case for the driver scheduler, we are going to submit 3 drivers. And we limited the number of driver slots in the cluster to be just 1, so that only 1 driver can start running and register application and so on. And we will perform the driver priority update to let the driver to jump in the queue. Okay, let me start playing the video. Okay. So we're going to submit 3 drivers, as I explained. First one with the priority value 3, second one with the priority value 2, and then the last driver with priority value 1. So if you look at the list, we see that the first driver that was submitted with priority value 3 starts running with the application registered. Second and third is still in the submitted state. So admin here is updating the priority value of the last application, last driver that has the priority value 1. And now, as you can see, the priority value has been changed from 1 to 10. So then it has the highest priority value in the pending queue. And when the first driver in application stops running, you see that the driver with priority value 10 starts running next. And when it finishes, then the last driver with the priority value 2 starts running and then finishes. Okay. So second case, we're going to explain, we're going to illustrate how the executor scheduler works. And for this one, we're going to use the fair share scheduling with preemption enabled with the timeout value set to 0. And for this one, we're going to use notebook jobs. So we have 2 Jupyter notebooks deployed, and then we'll update application priorities as the job is running to see how the executor scheduler interacts with them. Okay, so here you can see that 2 Jupyter notebooks are deployed, 1 for admin and 1 for guest. So we'll use the Jupyter notebook for admin on the left, and then for the guest, it's on the right. So we already have application loaded. And as you can see here, both of these notebook applications are already running with the same priority, same default priority value, 5,000. Okay, so let's start the job for both users. And we added the plugin for the Jupyter so that you guys can see, you guys can visually see the progress of the job. As you can see here, both of the jobs are progressing at about the same rate. And that makes sense because they have the same priority values, and each application is given 6 slots. So same number of slots to each application, so it runs at around the same speed. So then admin realized that his application is more important than the guest, so then he starts updating the priority values. He sets his application's priority value to 10,000, and then guest applications priority value to 2,000. So slots adjustments starts happening right away because preemption is enabled, and since it's a 1-to-5 ratio, as you can see here, admin's application is running a lot faster than guests. Should be about 5 times faster. So here, admin just randomly decided to lower the priority value of guest application down to 1, leading to 0 entitled slot for guest application. So then guest application loses all its slots, and then guest application stalls. So this is one of the reasons why authorization that we talked about earlier is very important for enterprise customers. Okay, so let's bring the priority value of guest application back to 2,000, so then it gets 2 slots. We also extended the open source Spark UI, so with the same set of information. As you can see here, we have the list of applications with their priority values and allocated slots. Okay, here we see that admin's application is now completing. And if we go back to the UI, we see that slots for admin's application at the bottom is now released, and it's now given to guest application. So then you can see that the guest application is running a lot faster. Okay, and then everyone's application finishes, and that's it for our demo. Let me get back to the slides. Okay, so if you liked what you just saw, we have some references here, so you can read some more details, or we have some trial edition of Spectrum Conductor, so you can play around with it, or we have a booth downstairs for IBM, so you guys can talk to us offline if you want more details. Okay. That's it. Thanks for listening.